We have a first-time DConf speaker again. Emmanuel here is going to talk to us about C++ interop. So,
hi everyone. My name is Emmanuel and I'm from Ghana. And I joined D last year working on C++ interop with Matthias, and it has been a great journey. So about me, I like C, I like D, I like C++. Those are the three languages I really like a lot. I write them every day. And I did SOC last year. Matthias was my mentor. And I'm currently researching into network buffer bloat issue of the packets dropping and all. My target for this talk is 2 people. Basically, D beginners, like the D programmers who joined D very early and have struggles with C++ interop. I used to link G++ compiled binary to D code on Windows because the spec didn't really specialize what it was. So I was struggling. I spent over a month. I nearly gave up. I was like, I'm not doing this again, and I stopped. And I think I was reading on a blog, and someone said, no, you should do it on Linux. And I was like, let me try this again. If I try and it doesn't work, I'm not coming back to it again. And I tried on Linux and it worked. And I was like, oh, okay. The other people are maybe the experts, the D experts, which are you guys. That will be showing you guys the state of the STL interop, the C++ STL interop, which is Linux, set, vectors, and then strings and lists and map. And on other map is not a finished work, but it's in progress. C++ interop is a global topic. I think every emerging language is trying to interface with C++. Rust, Zig, I know Carbon is doing, I know Python also does it, I know Swift also does it. But when you look at their approach, it's very complex. It's very writing a lot of wrappers and finding, like, they target as a very difficult topic. And it's like some do and they just give up. Some are investing a lot of time into interfacing with C++, and I'm sure they've not met D yet, but I'm sure if they meet D, they would stop what they're doing and come and do what D is doing. This approach is very simple. Basically, matching the C++ name mangling convention and also matching the function calling convention on the registers and the stacks. Also matching the virtual function table layout for single inheritance. So basically, those are the things you should look at when you're interfacing with C++ code from D. And you should, okay, at some point you're writing wrappers, but that will be very minute, not very deep as compared to what the other languages do. So I used to read a lot on the forums and the Discord. People really get confused about how C++ interop goes on, and I decided to use this to give a brief of how to understand what is going on behind the hood, what's going on under the hood when you're interfacing with C++. So let's take an example of a simple program you are running. Your compiler compiles your code. In terms of memory, your stack starts and your functions are being called on the stack. And if there's need for heap allocations, all those things goes on. And then your compiler generates assembly instructions, which is understood by your CPU and which is based on the instruction set architecture of your hardware you are using. And then the instructions go through the fetch, decode, execute cycle until the instructions are all executed. So basically, when you want to start C++ interop, I know a lot of people know C++, but if you depend on your C++ strength, you are going to fail with C++ interop. You should take your mind on D. So when you are doing C++ interop, you should always think D. Follow D rules, and I'm not trying to disobey D. If you try to think C++ all the time, you're not going to get it right. You're always going to struggle with C++ interop. The backbone of the interop is the semantic analysis phase of the compiler. Any C++ D interoperable routine must semantically agree. So basically, as I showed you here, that this approach is mostly matching the name mangling convention. So the semantics of whatever is going on C++ has to be the same on whatever is going on D before they can correctly communicate. If what's going on C++ is a little bit different, semantically from what you are doing on D side and you try to interoperate with them, it's not going to work. You are going to face a lot of issues. So basically, I'm giving a short recap of the C++ libraries, how most of them are designed. Majority of the C++ libraries are implemented with classes. C++ classes are value types. They are not reference type by default. D classes are reference types, but D structs are value types. So basically, if we want our libraries to be able to work in D, we should make sure that they semantically agree. And since these structs are value types and C++ classes are also value types, that's the best pair to work with. So when you are using your C++ class, always use your D struct. As I said, think D. So since D, you want value types in D, so use your struct and try to do your communication with your C++ class, and it's going to work very fine. So then you should know your D struct. When you're working with structs, I know D structs and D classes, there are some, maybe difference. The difference is maybe wide, maybe not wide. I'm not really, I haven't really used C++ classes. Most of the time it's D structs I use, but if you try to use D classes, it's not going to work because you like to copy. You like to make copies of your struct and all these things, and D classes is not going to give you that edge. Something you should notice from your D struct is when you are starting with your D struct, you should always be aware of the runtime you are using. As I said initially, I was trying to run G++ compiled code on Windows to link, but before I realized it has a different ABI, so if you are trying to use it on Windows, and I was also trying to import it from D runtime, which is distributed compiled. So the mangling of the interface was looking for MSVC compile library, but I was linking it with G++, which is not also going to work. So you'll be getting undefined references. When you want to use the default constructor from D, MSVC allocates on default initialization in debug mode, which you cannot realize in D, especially on Windows. But on Linux and Mac, maybe you can get your way around it, but particularly on Windows, it's not good to do that. So to be safe and freeze, just disable this. But you can use other constructors, like the copy constructors. You can also pass normal constructors, operator overloads. They all work. The destructors too also work. You can interface, you can call C++ destructors on your stack frame from your main function call. And maybe you need a few wrappers somewhere. C++ accepts our value arguments to const reference parameters, but D doesn't. So if you have a function like this in C++, void full const int reference a, you can just pass an R value of 5 or 6 without looking for a value that has a place in memory. C++ is going to accept it to work, but D doesn't accept it. So the most pragmatic solution is to write the same function by passing a const value as a parameter to your D function and forwarding your C++ function, which you have interfaced to C++. And then now the value parameter will now have a place in memory, and you can pass it to your extend C++ function, which constref would need, because constref would need a variable that has a place in memory. And so using this approach, you can easily call your C++. So if you call this function is also going to call this function, and in the end, you are going to get your C++ function working in D. Move constructors. I know move constructors do not currently work. You cannot call move constructors in D because D hasn't so found a way to do it. But if there's a need for internal move operations, I know I tried once with the std move in Phobos, and yeah, it worked for simple internal move operations. It does copy with very fundamental types, very small types. Copies that are not expensive, like int, copying 4 bytes from your memory is not very expensive as compared to copying huge structs and huge classes. So if there's any internal move operations, you are fine to use the std move, but calling the move constructor in this still doesn't work. So this is an update. This is a class, a C++ class, which has a pointer member field and all in a public scope, and a constructor that passes a simple integer and 2 integers, and a destructor. The first constructor allocates on the heap and assigns the value of the arguments passed to the constructor and maybe prints a simple allocating memory. And then the second constructor does not allocate on the heap, it just runs. And then the destructor destroys your resources allocated from your heap. So this is a simple C++ function, and we are about to see what actually goes on under the hood when you're interfacing with C++. So this is a simple destruct. And as I said, you need a class to extract pair before you can get it to work. As I said, the constructors work and the destructors also work. So you interface it directly like this. You call this to your ints, your 2 ints, and then your destructor, and then you call your object on your main stack. Now you first compile your C++ code. So this was done on Linux x86-64 architecture. And so you compile your C++ code with GCC, and then you try to link it with your D code. So your stack frame will be starting from the D main. There is no main function in the C++, and it's a single stack. So when there's a need for a D function, it's going to call the D function on the stack. And when there's a need for a C++ function, it's going to call the C++ function on the stack. This is a function I was testing. Calling this constructor, which is the first one, the one with a single integer parameter. And when I'm running it, I'm getting a segmentation fault. Why am I getting a seg fault? Because it's just supposed to run. Okay, let's go back to it. This is the function. It has some heap allocations in the functions. Do you think that would be the reason for the seg fault? Okay, so now let's see what is actually going on. Why we have our seg faults. This is the stack frame for the D's main function, and we know that D's main function has an object, and that object has a size of 1 byte. And so you realize that it calls memset and allocates 1 byte, offsets the base pointer on the stack, and allocates the address to RDI. It loads an effective address of 1 byte. The address in 1 byte offsets the base pointer and loads the address into RDI. Let's look at our C++ core stack for our int constructor. And we realize here that our C++ constructor is trying to move the value stored in 8 bytes, offsets the base pointer into RAX register for whatever arithmetic operation it wants to use it for. It's also moving RAX into the 24 bytes, offsets the base pointer. If I was supposed to, okay, so this is it. So the difference here, C++ is moving the value which is found in the memory 8 bytes, offsets your base pointer into RAX, and then D is loading 1 bytes of memory, the address of 1 byte of memory, offsets your base pointer into RDI for whatever operation it wants to use it for. Let's trace our stack, and you realize that the issue was when it was trying to move the value, which is in the memory address, offsets the base pointer to EAX. In the executable, it was having an bad access, meaning that the memory wasn't there and it was trying to access the memory which is not there. What would be the simple cause of this? This is because the core stack started from this main. When this main was trying to put OBJ on the stack, it allocated just 1 byte of the base pointer. C++ is coming into the stack with a function. That same byte offsets the base pointer. C++ wants 8 bytes, but D has allocated just 1 and has loaded it into the RDI. C++ is coming into the core stack, and C++ wants to access 8 bytes, offset the base pointer into RAX. Since D is the one calling C++ is acting more like a visitor coming into D stack, and D is like, hey, I have just 1 byte. So offset our base pointer, and C++ wants 8 bytes. Since C++ wants 8 bytes, it is not going to allow it to access that memory because that memory is not there. And the stack started from the main function, and then the constructor function we were calling was about to run as the next function downwards onto that same stack. That memory offsets the base pointer is not there. So C++ will not be allowed to access that memory. And so we are getting a seg fault. So let's look at the next function, the next constructor. The next constructor has 2 integer parameters, and so we pass 5 and 9 arguments to it, and then our obj is loaded onto our stack, and then we link and execute, and we are getting an execution success. It is running. The first one, we are getting a seg fault, but it's the same struct, it is the same class, but we are getting a seg fault this time. And you realize that this function also loads 1 byte, offsets the base pointer into RDI, and then it moves the 5 and 9 arguments onto your source and destination registers, and then it calls the constructor onto the stack. And then you realize that when it was calling it, here, C++ is not moving any value from the address offset the base pointer to any REX register. But when you go back to here, you realize that C++ is asking us for a memory of 8 bytes into the REX. But when you come to this side, it is not asking us. There's no instruction of a move offsets the base pointer to REX. And so since there is no request for that, there's not going to be a bad access fault. And so your program is going to run smoothly. So what are some of the takeaways we can take from here? If your C++ struct has 2 pointers and you want to pass 8 characters, which in the end is going to give you 8. You want to pass 16 characters, which in the end is going to give you 16 bytes, and you are going to get 16 bytes from C++ class, you are fine, because it's mainly a memory access routine, and so you don't have to care about anything. It's mainly a memory access routine. So if your C++ class has, let's say, 3 pointers, which is 24 bytes, and your destruct has, let's say, 2 pointers and has 8 characters. Once it wants to access that memory region and your D function has loaded 24 bytes, offsets the base pointer, you are free, because it's going to have that memory to do whatever it wants to do. So this is why you can pass 2 member pointers and they can pass 4 integers, or it's going to be 16 bytes and still get interoperable results. And it's mainly a memory passing routine, and that should be the most factored. So basically, that should be the main priority. But there are some trade-offs when it comes to thinking like this. Always make room for whatever C++ wants to come and do in the core stack. If C++ wants to come and sit down, make sure you give C++ a chair. If C++ wants to come and eat, make sure you provide food for C++, because if it wants to eat and there's no food allocated in D, it will try to take something which is not there, or maybe steal your food away or something from your house. So basically, make sure when C++ is coming, you have food for C. If C++ is hungry, you have food for C++. If C++ wants to drink water, you have water for C++ in your core stack, because it is the same core stack. That function is going to be loaded downwards. And wherever your base pointer is pointing to, that's the same base pointer address is going to use. Wherever your stack pointer is pointing to, that is where that same stack pointer is going to be is going to subtract it down to get a new space to operate. So it comes with a trade-off, safety. Some of the C++ libraries are very fond of not emitting that destructors, like especially on Linux. Clang compiler on Linux, yeah, most of them have a design that they will default their destructors from the base class, which is using getting your whatever container or library they are using, and then they have a way of using abstract classes and destroying the resources from the abstract class and not destroying them in the base class. And so you go and see the destructor defaulted in the base class, and you emit your symbols, and you go and you're not seeing any destructor. So what is the state of REI in the when C++ allocated heap is involved? As I was saying, some C++ libraries do not emit their destructors in their symbol table. Some of these libraries allocate on initialization. So you have your heap memory, you have some resources there, and when your stack is being cleared, you still have some memory in your heap, and it exposes your code. It makes your code very vulnerable to whatever attacks they want to. So in C++, they have their way of using REI to destroy resources allocated on the heap. But what happens to it on D? You can either use destroy on destruct, or when your struct has ended its lifetime, I know that the destructor is called internally in D. So let's find out. Okay, so this is a simple C++ class. Okay, this is the same one with the destructor commented out. And then I call the first constructor, which allocates memory. Okay, and with the second one, and I've cleared the destructor. So now there's no destructor. So we are assuming the C++ destructor is not emitting its symbol. And then I have my extend C++ struct. And here I decide to include my field with the pointer because C++ class also has a member pointer to it. So let's say I call the second constructor, the second function, and then I pass a 5 and 9 argument to it. I try to run it. And note this test is for Linux, most reliably on Linux. And then LDC2, and then I compile my C++ library into object files and I link it. And then I enable my address sanitizer. Now I execute D, and obviously you are going to have 4 bytes leaked in memory because I allocated an integer. I assigned an integer to my memory allocated on the heap. So we are definitely going to have 4 bytes leaked in one allocation. So now let's call destroy on our struct without reinitialization. Can someone tell me what do you think will happen with this? Will the heap be destroyed? Why don't you think so? Because destroy is going to the memory address, which is going to be held by the C++ pointer on the heap. When you are calling it on the stack, that pointer will try to come and access the memory in which this P lies, below the base pointer, offset the base pointer. So, okay, so definitely, even if you call destroy on your destructs, you are still going to get your 4 bytes leaked in your allocations. What could be the best solution for this? So I'll come to this at the end of my talk. Let's go to the C++ STL. When you want to use the C++ STL from D, you can either think of looking at the code implementation and re-implementing everything from scratch in D, or interfacing it and using it from D. Each of them has their own problems. If you are re-implementing, you are not going to get a lot of it, and you're not actually going to get what it's actually doing. You would have to take away with a lot of things because D does not agree with some things on C++ and a whole lot. But if you are interfacing it from D, you want to use it, you want to get its full function, what it's designed to do in C++, and you want to get 100% of it in D, then you should be ready for some troubles. That's what we're about to look at right now. Linux is your best friend. Ubuntu is your best friend. When you're linking with GCC compiled binary, you get most of your symbols you desire, and the symbols are easily linkable, and interfacing this is quite easy due to the simplified CSX Titanium ABI, and it's not very complex. So if you're on Linux and you just compile your library, you check your symbols, you can get maybe 90%, 80% of it, and maybe you add a few implementations, you are good to go. And then Linux might betray you a little, especially when we clan compiled binaries. The libc libraries do not like to handle the allocation with the base class destructor. They default the base struct and go and destroy the resources in an abstract class, which is used to derive the base class. And so if you do not keep very tight track of those, you are going to leave your code vulnerable to leaks. Windows is that one friend who decides when to be good to you. Yeah, Visual C++ mangling scheme is very complex. You can find it very difficult to even call a single C++ function on Windows just because of maybe a public or a private you didn't declare, or maybe a class or a struct, or maybe the layout of your symbol when you're trying to interface it. Because if I try to explain the Visual C++ mangling, I'm not sure I'll get time to finish my talk. So there are some few trace points when finding it hard to debug your symbol interfacing. So look out for access modifiers. Visual C++ mangles private fields and public fields differently. So if you create a simple class in C++, let's say void full in, let's say, class A, and the class is private by default in a C++ class, it is going to mangle it differently. If you declare public to it and you try to call with the same interface you are using, it's not going to work because the Visual C++ mangling is going to mangle it differently. Especially on Windows, if you are trying to call a C++ class, make sure you use the extend C++ comma class. I'm sure it'll be on the spec. I think I added it, but I don't know where it is. So, and around time, macOS is your worst enemy. When we started the project, we were testing with macOS 11, 12. Yeah, it was 11 and 12, and you would spend time and you would maybe call a lot of your symbols and maybe get few not emitted and you re-implement them in D and it will work fine. And immediately add macOS 12, your code start breaking and you go and check and macOS 12 emits some functions as local text symbols, hence not linkable. The function that you were getting on 11, you are not getting them on 12. And now you have to maybe go and implement them. And even sometimes the ones you already implemented on 11 even breaks. Because I don't know, I'm still researching into it to find out why, but I personally myself, I don't know why. So maybe if someone can volunteer to explain to me, but sometimes you will get your function which is working on macOS 11, which you re-implemented from D breaking, and sometimes function which you get a symbol very right and it breaks. And then you implement them again, and then now you go to macOS 13, and then you go and the function that was not global in macOS 12 will now become global in macOS 13, and then another function that was global in macOS 12 will not even be emitted at all. And so you realize that all your work you did with macOS 11 is now waste, and you have to go back again and then redo everything again. And macOS 14 doesn't really care about you. It emits what it wants and what it doesn't. It can decide not to even emit at all. Maybe for a particular library, you can even on your own written library, you can get very different functions being emitted for symbols which you can easily pick on macOS 13 or macOS 12. If you're using macOS, you should maybe be very, 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 very alert when you're using macOS to interface with C++. It's a very stressful journey using macOS. Currently, the work done initially removed core.stdcpp from D runtime. Now we've separated it into its own package. So you can look it up in GitHub under the stdcpp dlang repository, and it's currently managed in that package. The containers are worked on vectors, list, and set. std set only works on Linux and string. And these are our terror runtimes which target. We will still be going on to maybe BSD and other runtimes in the future. Your primary C++ compiler targets should be on Windows. You should target Clang and MSVC, on macOS Clang, and on Linux Clang and GCC. So when you are testing, every container has its own size. So we cannot be always doing the hard coding to maybe verify some C++ and be like, okay, it has 12 bytes in C++. So we are set to check if it has 12 bytes. And then the capacity is also different, even on different runtimes. And I think vectors is 24 bytes on Windows and it's like 16 bytes on, I've forgotten, but the sizes differ on each runtime. So the best is you hacking your C++ compiler which you are using to actually give you whatever size or capacity to use, which is a very modest way of getting this simple test done. Okay, with templates, the STLs are template libraries. You should have a C++ file that has your C++ templates instantiations, and this should basically, maybe for a list, if you want a type int, you should get your template class std list int. If you want character, you should get your template class std char, and it's going to emit all the symbols for you, and you follow up to link to it basically. And this also is a test of the size of every container. So for string, for list, for vector, and for set. And then when you compile this and you link it to your code, your interface code in D, you are going to actually get your C++ function running in your stack, which was called from D. If you want to have a standard C++ file which has all our instantiations, we can actually instantiate our template classes for all fundamental types, for character, for ints, for doubles, for floats, for all the fundamental types we have in D, so that if you are using your instantiations and maybe you have to assign a vector to, let's say, a float, it's not now that you are going to a C++ file to go and instantiate. Maybe you have it somewhere you can easily link to. The types are not only fundamental. You can have a vector of struct, a vector of classes. It's not only vector of int. There are a lot of names you can have for your aggregates. You can call any name to a vector. It's not like an int, an int, an int. You can call any name, and the C++ compiler uses the name of the struct during mangling. We want to have a let's say, a file that is going to generate your C++ libraries for you. And let's say you have a struct A and you want to use your struct A in D for, let's say, vector, and you want to call it from C++. Basically, you need your struct A template class std vector A, and then you compile to give you your symbols, which you can link to. Should we be doing this for every single aggregate? If you are writing million lines of code and you have like 100 structs and you want to get your symbols for your struct, and all the time are you supposed to be doing this? Because there are infinite number of possible names for your aggregates? No. I wrote a simple program in D which aids in emitting your symbol for you. So I'll be doing a short demo here. I copied the instantiations here, and then I had a way of the program generating your symbols basically from your aggregates and loading it here. And then that same process, starting another process by compiling this code for you to get your objects in whatever code you're using. So maybe in the future, I will see how we integrate it very well, but I've still not gotten a better name for the program, but I've called it manglecpp. So let's say if you are working with vector and you are passing a struct to your vector class, and then you want to get your symbols, you can basically just do a symbol like manglecpp. And then since it's a vector, the switches I was using were more like a VC for a vector class, a VS for a vector struct, an LS for a list struct, an LC for a list class, and a set C for a set class, and a set S for a set struct. When you're having, let's say, a vector of struct A, you can just call it like this, VS, which is a vector of struct A equals A. Right, so this is a simple program you can use, and when you run it, you realize that, VS equals A. Okay, so when you run your program like this, manglecpp, that's VS, so meaning for a vector struct of A, you get your struct A and your template struct std vector appended into your TPP file, and then the process runs it to produce your access.o object file, and then you can easily link it to whatever code you have. So I feel this is a program that we can use for interfacing with our C++ libraries that are included with aggregates and not only fundamental types. Thank you.
The mangling on macOS, is it the Apple client compiler that does that? Completely different, or the symbols on macOS? Did you check using the stock?
It was one compiler, the single Clang compiler, which was, and I tried it for different versions of Clang, and it's still the same. It's like OS 14 is different, OS 13 is different, 12 is different, 11 is different.
Would it help to use GCC on macOS or not?
GCC, I haven't tried it, but maybe I'll try it and see.
Okay.
So I've probably done more work on this than anyone. Firstly, congratulations for jumping in on this. This is a ridiculously dense woods full of bears and terrible creatures. And it seems like you just jumped straight in the deep end. So good work. I hope you keep it up.
Thank you.
I was trying to keep a mental track of a whole lot of details through there, but there was so much to talk about. So I think really we just need to sit down and have a really long talk. Yeah, I don't think anything else I can say right here, right now is going to add value for the listeners, but there's a lot to work through there. Okay. I think a lot of what you're running into is the result of inlining on the C++ side, and therefore symbols not appearing to link to. And so mangling stuff is almost all compiler bugs, and they just need to be fixed. You showed a whole chunk of what appeared to be an ABI mismatch that could just be bugs, or it could have been some sort of a declaration failure. I'd like to see your specific test case, and we just should sit down and workshop some of this stuff.
Okay.
Cool. Thank you so much.
Welcome.
For our first project, you sure picked a tough one. I admire your courage in tackling this. So, I just think you're doing a great job.
All right, words of encouragement. Well, if we're not going to have questions, I think words of encouragement are even better than questions there. So thank you again.